So if, however, this is curved, but if you cut it, so this has a very beautiful this regular shape. So either circle or just this kind of this oval. But so if you take a look at the bigger picture, so this guy is a curve. It's not a straight curve. Not a straight. This is a beam. It is a curved beam. For curved beam, something is different. Something is different from the straight beam. So you can see, okay, on the first one, a neutral axis and a centroidal axis, they are not coincident. So if this beam is a straight beam, so this line will be the neutral axis, and this line will be the centroidal axis. So that's great. However, because this beam is curved, this guy still the centroidal plane, but it is not. It is a neutral axis. Right? The neutral axis. So for this problem, so this is center, and we have the inner radius, and we have outer radius, and so we also have so this is a neutral axis. Okay, so this is a neutral axis, and this is CO, and this is CI. So these are the minimum. These are distance, maximum distance, from the neutral axis, from this side and this side. So we have a bending moment. And if we take a look at this one, so here the difference between so this centroidal line and this is neutral line. So we use this E to denote. And so we have this height of H, and we have RC, and we have Rn. Rn is the neutral axis, radius of the neutral axis. So this R is a generic, is the radius of generic point. So be very careful. You need to put a question mark. So this one is I'm very positive that you have never seen this problem. Have you? Okay. So be careful when we learn new things. So bending stress does not vary linearly with distance from the neutral axis, and so they are kind of different. For this one, right? So and how to calculate? So this is and how to calculate. So this is a notation for all these symbols. And be very careful, guys. So how to calculate? So this is Rn, and you need to use this equation to calculate this Rn. So this Rn equals the cross-sectional area divided by this integration. So this is R. Okay. So so this is R. And dA, and from this is you need to do this integration, the stress distribution. So after you get this Rn, and you can do the stress distribution using this equation. M is the applied bending moment, and Y is so here is a Y, guys. Here is a Y. Y is the distance between the point and the neutral axis. Between this Y, before you know this Y, you need to locate this Rn first, okay? And get this Rn first, and then you can calculate the distance between the point of interest and to the neutral axis. So E is the distance between the neutral axis and the centroidal axis. So this is, you can see Rn is the most important one. So after you get this sigma, for inner surface and outer surface, and you can use these two equations to calculate. So keep in mind, one is a positive, one is negative. Questions so far? So this one is the first step, and you need to calculate. And then we take look at here is one example. Okay, so this is for example I go very quickly. So this is a hook. This is a hook. So even though if we just draw this is draw imaginary is a plane. So this one is very beautiful. This is a rectangular shape. However, so the whole beam it is curved. Right? As a result, neutral axis and this is a centroidal axis. They are different. So this is a center, right? So this is a center. At the very beginning, I do not know. I just denote this one is Rn, neutral axis, radius of neutral axis. So this is RC, okay? So this is RC centroidal. Centroidal is usually in the middle because this is rectangular shape is very regular one. And so this is the inner radius. So this is my outer radius. So this is a height. And so how to calculate? And this is Rn. So this is how to calculate this Rn. We use this equation, right? So you will use this equation. Rn is calculated. This equation, put this equation here first, and A is calculated as the base multiplied by height. The base is 4 inch, height is 3/4 inch, and BH we just put the BH here, and then we look at here. So this is integration. This integration is about this R. That means from inner radius to the outer radius. You can see lower limit and inner radius, RO is outer radius. And so dA, okay? And dA here, you can see dA. So dr, this is dr. So this is a dr. This is dr for this infinitesimal small area. So this is a dr. So dA equals dr multiplied by this one, right? Multiplied by this. And you can see this, and you can dr. This is a dr multiplied by b. And b here, they use this one as a b. I'm okay, right? If we just look at this one, this might be, so this is my h. So as you see, b multiplied by dr equals dA. I want you guys to know that. So they use this one as a b. This is a base multiplied by this small height equals this is the shaded area. So this dA and then over dr. This b cancels this b, and I know that 1 over r dr equals log r0 ri. So this is outer. This is the upper limit. So this is a lower limit. So 1 over r dr equals is a log. This is log r, right? This is a log r. So this is ri. So this is ro. So this gives us log r o minus log ri. So as a result, it equals ro ri. Right? Okay, so this is we calculate this Rn, and we just plug in and we calculate so this value. So these are first step. Calculate this Rn, and after we calculate this Rn, and we can calculate this E. Hey guys, by the way, guys, when I teach this one, I want you to pull out use the pencil or pen to draw down important things. Okay, so. Engineering discipline is different from the liberal arts. Liberal arts is a lot of talking, a lot of reading. But for our case, we are handling numbers, units. And so that's the reason I want you guys to jot down all these things. So first we get this Rn, and then we can calculate this E, right? And we just put this in this equation. And we can calculate that this is a sigma, and sigma we have the stress here, but why we have this I divided by A, guys? The reason is that, right? So still it is a countertractive force applied at this point. So we are progressing on this plane. So this force will have two effects. One, and so this guy is going to pull it vertically. Two, so this guy will generate a bending moment. The bending moment equals the product of this F and the effective distance between this point and this center. Then this M is going to bend. So this is a hook. at this point. So that's the reason we have two things here. We can just move F prime equals F in magnitude, and then we have bending moment. So that's the reason. And when we calculate the stress, so this F divided by A is the tensile stress. So here it is bending, because of bending moment, we have a stress. This is also normal, the stress. That means and the perpendicular to the surface. That's the reason we can put these two guys together. Right? So you can see we can just draw a curve, put these values inside this here. We can see the sigma is changing with respect to R. Questions so far? So in a nutshell, when we handle this curved beam, the most important, the foremost step is to calculate the Rn, the neutral axis radius. If you make a mess up that one, I'm 100% sure all your calculations will be wrong. All right? Be very, very careful about that one. How to calculate the Rn, the neutral axis radius. Now, this is the formula for sections of curved beam. So this is some people they have done this for us. Whenever we handle this is either is a rectangular or the trapezoid or this is a T shape, and we can come back to use this sheet and to calculate our Rn directly. Questions? No questions? And then we there is for the circle, the fourth circle, and for this is I beam, and for this one is this is circular, not circular, a rectangular. This is the wall, this is the shape. So this is alternative calculation for the E. E is the difference between the Rn and Rc. Then some people they just use this one. So this is I divided by RC. A is the cross-sectional area. RC is the radius of the centroidal line. Right? Centroidal line. I is area movement inertia. So this one is you can use this one, but as it shows, it is just approximation. Be very, very careful. And when we do research, and we will not use this one, we need to use our analytical equation to calculate. Okay, when we do research. But for estimation purpose, we can just use this approximate solution and to guess. You have sense, guys? When we do research, and you need to use the analytical solution to make sure every step you get the accurate result. So here is an example. I'm going to illustrate. I'm going to skip this example, and you just take a look. And then we talk about contact stress. Contact stress is contact stresses that are commonly used in the machine design. Okay, so because when we design something, always with some components they are in contact with each other. So for the contact stress, two bodies with curved surface and they press together is one case. And point or line, the contact changes to area contact when you just cut the material and using the tool. And stress developed are three-dimensional. Okay, so physically, and the stresses they are three-dimensional. The 2D stress is just a simplified version. And we call contact stress or Hertzian stress. Hertzian is a genius, and he developed this stress. The common examples, for example, the wheel loading on the rail. So this is contact. So making gear teeth, the two gears, they are meshing each other, and rolling bearings. The rolling bearings, so this is outer ring, is inner ring. So these two guys, they are rotating with respect to each other. But we have a shaft inside. The shaft will carry some load. That's the reason this inner ring is going to press this outer ring. So we will see a lot of this contact stress, at least for the gear. When we talk about the gear designing, when we will talk about the contact stress. So special contact stress. So this is two solid sphere or diameter of D1, D2 are pressed together. So circular area of contact radius, and we can use this equation to calculate. So this is very, very accurate. This is analytical solution. So Young's modulus, E1 is the Young's modulus of material 1. E2 is Young's modulus of material 2. U1 is the Poisson ratio of material 1. U2 is the Poisson ratio of material 2. D1, D2, they are the diameters of these two guys. F is a force. This is a very, very accurate one. This is analytical solution, analytical equation, and this A is an analytical solution. So spherical contact stress can press them together. But you can see this here is in the contact stress and 2F D1, D2. So this is a hemispherical maximum stress at the center and calculated using this one. So maximum stress on the z-axis and principal stress sigma 1, sigma 2, and they are equal this one, and sigma 3 equals this. And for Mohr circle, you can, if you are interested, you can just use a Mohr circle to represent sigma 1, sigma 2, sigma 3. So I will not test your understanding, but I just want to show you that, and we have a slide here that can help you with. And so this is spherical contact stress, distance from the contact surface, and how the sigma x, y, z, and tau maximum changing. So this is cylindrical. The previous is a two bolt, two spheres, and here is a cylindrical. And they are this is a B, the hollow width of B here. The maximum pressure is given also. Here is elliptical. So here are the three stress values, and this is a distribution. I just keep in mind, okay, whenever you need these equations, you can come back to see some people have already done this one for. Any questions regarding this whole slide? This whole slide talk about the stress, about the strain, and finally we also talk about the open seam wall structure, the seam wall structure, and then we talk about the band, this curved beam, which is the most important one for this slide. If no question, we move on to the next one. So this is lecture 3. This one is talk about the stress. Then we talk about the deflection. So the stress is the stress, and deflection is the deformation, geometrical deformation. So the first we talk about forces versus the deflection. So this is just use a beam, okay, this is a beam to illustrate. So elasticity means that the property of material that enables it to regain its original configuration of the deformation. Elasticity means that after you apply the load, and so this is the structure deforms, and then you remove the load, then the structure recovers its shape and the size. So this is elasticity. Right. So here the spring is a commonly used mechanical element that exerts a force when deformed. And so for this is a beam, we can just treat this beam as a spring. So this is a linear spring. If you apply this concentrated force in the center, and we will see it deforms this way. And so this is the deflection of this point at which we apply the load. So you can see if this is elastic, the F and Y, so they will change proportionally, the straight line. So this is a nonlinear stabilizing spring. If we apply a load, so we have a corresponding Y. If we change the F, and so this Y will be changing. However, this F and Y curve is nonlinear. Nonlinear means that so it's either this is a large deformation, which is a geometrical nonlinearity, or the deformation of this material is elastoplastic, not just elastic. So this is nonlinear softening spring. So this is kind of strange. If we press it, it pops on. So this is kind of interesting, right? Here, this is how this I changes with this one. It goes this way. Questions? So this one, when we use a special material, the commonly seen material, they have exhibit this kind of phenomena or this kind of one. But some special material, they have this. Questions regarding this slide? So you know the elasticity. Elasticity means that after you remove the load, the structure recovers its size and also shape. The spring rate, we have a spring rate here. Spring rate is so if we have f is a function of y, and spring rate is the differentiation is the derivative of f with respect to y. So if this k is constant, and we can just write f and y. So this is spring constant, right? This is we call the spring constant, or this is a spring rate. Questions? We know that, right? Okay. So this is actually loaded. This is the stiffness, and the total expansion or contraction of uniform is a bar in tension or compression. If we have a bar, not just this is the cost. This is spring. This is the spring. Or the beam is a verb beam. The beam can be treated as a spring. So, however, if we have a beak, this is the cross-section area, and then we just either apply tensile load or this compression load, and we can use this equation to calculate the deflection. So F is the force, L is the length of the beam, A is the cross-section area, E is the Young's modulus. And for that beam, if we still use the spring constant to denote the ratio of F with respect to delta, and this K is denoted using this equation. One more time. The F is the load you applied. L is the length of the beam. The A is the cross-sectional area of the beam, and E is the Young's modulus of the material of the beam. Question? The torsional, this is previously we talked about tensile and compression. Now we talk about the torsionally loaded state. If we have a beam and we apply the torque, so this guy will be twisted, and this we have a twisting angle and or twisting distance. So for this one, we're using this equation. And so actually we talk about this tau, what kind of stress we have when we apply load in our previous lecture. So this is theta here. If I know the torque, how can I calculate the corresponding theta? How the angle I twist? This is a material, twist this structure. So this is TLTJ. So T is applied load, L is the length of the beam, and T is the shear modulus, which is related to Young's modulus and Poisson's ratio. And this capital J is a polar moment of inertia. So for the special case, if this beam is a round beam, a full circular beam, and the J can be calculated using this one, then theta can be simplified using this equation, which includes the diameter here. And then I would get the theta, okay? And then the spring constant can be treated as T divided by theta, and the theta contains T here. So we can have, this is our constant for the torsionally loaded state. Questions? No question? So bending. So for the bending, this M is a bending moment. So the curvature of the beam, okay? So the rho is the curvature of the beam. Young's modulus I. So from mathematics, curvature of the plane beam and it equals this equation. Y1 over rho and dy dx, y is the deflection. And you can just the slope of the beam at any point x along the length equals dy and dx. And finally, so m and ei can be treated as dy and dx, the second derivative of y and respect to x. Keep in mind, y is a deflection. Y is the deflection of the beam. So here is a beam. If I apply a load, it goes this way, right? So this is the deflection. This is a Y. So beam deflection by superposition. Have you guys ever heard of the superposition? Have you guys ever heard of? The principle of superposition means that if we have several loads, for each of these loads, we have a solution. Solution means that deflection, stress, right? So then if I apply all these loads together simultaneously, and then the results will be, the solution will be the sum of all the solutions based on each of these loads. This is called superposition. On superposition, the assumption is that the material is inelastic and a small deformation. Can you write down this? The superposition's assumption is the material is inelastic and the deformation is a small deformation. And large deformation, that is another nonlinearity. They call it geometrical nonlinearity. So separated parts are solved using any method for simple load. Many load case and boundary conditions are solved and available in reference such as so this one. So you can see each effect is linearly related to the load that produces it. So they are talking about the both elastic and this is a small deformation. A load does not create a condition that affects the result of another load. The deformations resulting from any specific loads are not large enough to appreciably alter the geometrical locations of the parts of the structure system. So there are the assumptions. To be simple, okay? So to be simple, the superposition, you should have the small deformation and also the elastic. So we can guarantee that from the perspective of material, it is linear, and also from the perspective of geometry, it is also linear. Questions regarding this slide? No question? So this example, I will not go to talk about this one in detail, I'll just show you, guys. This R1, R2, if we apply load, we have reaction 1, reaction 2. So then we have, this is a uniformly distributed load, and then ask you guys to calculate and the deflection and this uniformly distributed load along with this concentrated force. And how to do that? If we use the principle of superposition, and we will do two things. First, we only apply this F, this load, concentrated load. We know the deflection at each point. Then we just remove this F and we apply this uniformly distributed load, and then we get another set of solutions. Then F and this is omega. We apply them together, and then we just put the results together, their individual results together. That will be our total results for when we apply both F and omega on this beam. So here you can see, okay? So this is for the concentrated force only. So this is for the uniformly distributed force only. And you will know the YAB, why we have YAB, YBC, YAB, YBC. So YAB means that if the point is located in this interval, and we use this equation, and YBC means that if the point is located in this interval, and we use this equation. whenever you see the concentrated force, and you are supposed to differentiate on these two light segments. Okay? Because physically speaking, the concentrated force is the singular point. You need to differentiate the definitely. And for these two guys, either this is point B, because point B belongs to this point, this interval, and point B belongs to this interval also. For point B, if we use either of these equations, you are supposed to have the same identical result. For here, this uniformly distributed load, and we can get one equation that is applicable from the very, very left end to the right end. As I said, only for the concentrated force, and you need to differentiate these two intervals. One is to the right, and one is to the left. And then you just put them together, okay? So I will not talk about this slide. And the street energy. And then we talk about street energy, guys. And have you guys learned street energy? No? Okay. The street energy, you can see the street energy is external work done on the elastic member. In deforming, it is transformed into street energy or potential energy. And the street energy equals the product of average force and deflection. So U equals half of F multiplied by 1. And K is a constant. K is a spring constant. Okay, so you do not know the street energy. Okay. For the axial loading, and we apply for axial loading, okay? For axial loading, and so this spring constant axial loading is a tensile, either tensile or compression. So the K, the spring constant, equals AE divided by L, right? So this is what we just talked about. And then this is U equals the street energy and equals F squared L 2AE. So this is if the spring constant is a constant, if this is a beam has a uniform, this is the cross-section area throughout. So if we use this equation. However, if this A is a function of this X, and we will use this one. So which one is more general? That means the cross-sectional area is changing and with respect to X. It's not constant, and you need to do the integration. Okay. So for the torsional loading, if you apply the torque onto this beam, and how to calculate the street energy that you have made, we use two equations. Still, so this one says that so this is G. I'm sorry, this is J is constant. J is constant is per moment of inertia. That means the cross-sectional area is a constant and throughout this beam. So this one and the J is a function of X. So that means the J is changing and with respect to this location in the X location. Question? No question? So we use this one for the uniformly for cross-sectional area throughout the length, and we use this equation for the beam that for which the cross-sectional area is changing. Shear loading. So here is the shear loading. This is the direct shear. Okay, shear loading. You can just do it this way. This is shear. And shear loading. 2AG and the G this area. If the area is changing also, and so this is we use this integration. And so for bending loading, for the bending moment, it will bend it, right? If this one is uniformly distributed for the cross-sectional area, and we use this, otherwise and you need to use this equation. That means this is my x-axis. Keep in mind, right? So this is my x-axis. If my I is constant with respect to x, that means along this axis direction, and I use this one. Otherwise, I need to use this integration. Some common string energy formula for the transverse shear. The transverse shear is a big is very, very complicated. So we use this transverse shear C, and C is related to the cross section area. So this one we have the factor for different cross section area. So once